binary terms,
Yes, yes.
right? Oh, let's throw this out because you accelerated. It doesn't
Yeah, but
count anymore.
you see, the special relativity, it's an abstraction. It's absolutely abstraction. It's not, even if you believe in this relativity, the special relativity does not exist because everywhere you cannot have a perfectly constant speed. So it's just acceleration everywhere.
Mhm.
So it's not possible to have exactly constant speed, you know, in this
Uh,
universe.
I'll tell you something. I'm working on a new book, and I decided to just, I've been avoiding dealing with general relativity because I see it
Mm,
as a very big
mm,
project. It's a lot, maybe more than I can chew.
mm,
That's an English expression, biting off more than you can chew. Um, so, I didn't want to go there, but I actually do a little bit in my next book. And
mm,
one of the things I noticed is in Einstein's, you probably heard it described as his happiest thought, where
mm.
he realizes, if, say, an elevator is in free fall and you're in there, you feel weightless and you can't tell the difference
Exactly.
between that
Yeah.
and so it feels the same, right? That's about a feeling,
Mm.
right? Your experience, you're
Yeah.
weightless, you're
Exactly.
floating.
Exactly. It's about
Okay.
feeling.
And you're in this little box. You can't see outside of it, right?
Yeah.
And that's the idea. You're going based on how you feel and not what you can see.
Yeah. So if
Mm-hmm.
this feeling is giving you in imaginary way, the feeling you have an absolute frame of reference in order to resolve the twin paradox is just an imagination, is not real because it's not really giving you an absolute frame of reference to
Mm-hmm.
resolve this paradox. It's not possible using acceleration. I have a feeling, I have a feeling about this, but it's not real.
Mm-hmm. But where I'm going with this is that it's not the feeling that helps you resolve what is real
Uh,
and what is not. You have to think about more things. There, you can look with your eyes. Is another example, right? To see
uh,
whether or not something's moving. So what Einstein basically does is he's saying there's no difference between co-acceleration and not acceleration, right? So if I'm accelerating at the same speed, or sorry, not speed, but rate, I guess it would be better to say, if I'm accelerating at the same rate as the elevator, the air
uh,
inside the elevator, everything inside that elevator is accelerating at the same rate, that means uh, we can say it's not accelerating, right? So the elevator's in free fall, we can say it's actually an inertial
exactly,
motion.
exactly.
I say no. I say there's a force, a real force. Gravity is a real force.
Uh,
It's pulling on elevator and you and the air inside the elevator, everything in that local environment at the same rate, the same strength, if you will. Everything's accelerating the same amount in the same direction. And because of that, you feel nothing. That's all.
yes.
It's so the it's easy to explain why you feel nothing. It's not because you're not accelerating. It's because everything is co-accelerating.
Uh,
So it's a pretty simple idea, but the way
yeah,
we can
everything at the
differentiate
same rate. Yeah.
the way we can differentiate between accelerating frames and non-accelerating frames is we can look around and we can see what is
Uh,
moving relative to what and how is that changing over time.
uh,
And if we do that, we realize we can keep our old concept of acceleration, which was based on motion over time.
uh,
So before Einstein, we believed that acceleration was a function of motion over time. It was the second derivative of position over time. And I think we can keep that. I think we should keep that. Right? So isn't that amazing to think that, say, you on the other side of the world, me on the other side of the world, we are maintaining the same distance the whole time we're talking. But according to Einstein, we're actually accelerating in opposite directions.
uh, exactly.
Acceleration has nothing to do with motion.
Yeah.
I say it does. That's all.
Yes. So if I am in an elevator and I have the same acceleration, with the elevator, then for me the elevator is not accelerating. So it's zero acceleration. From my point of view, from my frame of reference, the elevator is just staying. And I feel nothing. I don't have this feeling it's a force there or it's something we are moving or nothing.
Yeah,
I
but
feel no acceleration.
if it's a glass elevator and you can see out, then you can see that you are falling.
Yeah,
And you can
yeah.
see that you're
In this
being
way,
pulled by a force.
yes.
So,
Yes, but this is proving uh, in a way this acceleration is not an absolute frame of reference. So it's not resolving at all the twin paradox. It cannot resolve it because
no.
it's not existing. It's something which exists, I think, just in the perception, not in the real world.
Unfortunately, this happens a lot in politics and in science, where it's hard to defeat an idea because there's too many things wrong with it.
Mm,
So, and this is the way it is with Einstein's theories,
mm,
both of them. There are too many problems with it. You can't pick one. You can't isolate one. There are
mm,
just so many problems.
mm.
You lose focus when you try to deal with it. It's this enormous thing with lots of
Exactly.
problems.
It's very hard to catch the whole picture and
Yeah,
understand where is the problem. Exactly where is
yeah.
the problem of this theory. To
And so,
understand it.
because of that, it actually makes it easier to make lots and lots of mistakes than just to make one mistake. Everyone would naturally think it's easy to make one mistake, but making 10 mistakes, that's hard because that requires a lot of luck or, lots of stupidity or something, right? But actually, no, it's much easier to make 10 mistakes
Uh,
than it is to make one mistake because when you're in an area where there's lots of assumptions that have to be made and it's just very difficult conceptually, the mistakes can start to gang up on us.
uh,
So that's how it is.
okay, the way I understand this problem with relativity is like this, like I saw in this podcast we made. Um, if I am in a spaceship and I reach maybe almost the speed of light, I see from Earth, for example, or if I take in consideration the twin paradox, doesn't matter. Um, from Earth, my clock is freezing completely, so the time is stops.
Mm-hmm.
And if I'm in this paradox, twin paradox, then it's the clock on Earth. It's freeze for me. The time is stopped.
Mm-hmm.
But the guys on Earth are living normally. So this relativity does not exist in if I imagine this experiment. Relativity is not something which exists in reality, but it's perceived like it's real because I think this the main problem with this relativity it's because it started because for any system of reference or for any observer or for for any observer in the universe the it's a limitation for information which is perceived. We can perceive information with a maximum speed of light. I don't know why. Because I think because it's the forces inside the between quarks or
Mm-hmm.
between atoms or between different particles are the information there is transmitted. The forces are transmitted
You know what?
to yeah.
I want to stop you there because
Okay, okay.
there's a lot that
Yeah,
you said, but I
yeah.
actually disagree with the most of it. And the reason
Okay.
for lots of reasons. One of them is I don't think there's a speed limit
Mm,
on, say, motion. Uh, Practically speaking, yes, if you want to communicate with somebody far away, the fastest way you do it is with a radio transmission signal. But I
mm.
don't think that in principle that's the fastest.
Okay, okay.
Another thing would be when it comes to sending information. I don't think that molecules, particles, whether they're entangled or not, I don't think they actually communicate. So I think that information is something that exclusively exists in the realm of life. So only organisms actually communicate. Uh, Before life existed on Earth, there was no communication anywhere in the universe,
Mm,
unless life existed somewhere
yes,
else as well. But
yes.
I don't think I think that information. So when we talk about information, we can mean lots of different
Um,
things. Sometimes we mean real information, like the stuff that we understand through, say, information theory, like Claude Shannon's information theory. That's one type. There's also quantum information, which is completely different. And then, like, because you can't copy it, you can't delete it, you can't uh, hide it, you can't edit it, etc. Other things like there's something called what I call Laplacian information, which is sort of
mm,
like the idea that if you knew everything about the present, you could know everything about the past and everything about the future, which isn't even true. But if it was true, then what you would have is something they call information. But I say that's not information because it's not symbolic representations. Anyway,
um,
that's it really matters what we mean by information. If we forget what we mean and we keep talking about it and we keep,
um,
I have this equation that measures it and all this stuff. In order to know how to apply the equation, we have to know what the concept means and we have to keep track of what it means. And I think the big problem with physics is all the concepts like information, entropy, probability, even speed and time. All these concepts keep changing their meanings, and we're not keeping track and properly dealing with the concepts. Instead, we stick with the mathematical equations because they're simple, and we worship them, and we think that we've come up with a beautiful, elegant theory that makes sense because mathematically it makes sense, but underneath the concepts don't make sense, and we need to
mm,
clean up this huge mess of concepts that underlies physics.
mhm. Okay. Yes.
I know.
What I want to say is, in the real world, I make a separation between what is you saw the dialect movies in the
Mm,
last time. So if I understood well what they said, it's like you have the reality where the speed of light is nothing. It's just a normal, usual speed, nothing. Just like any other speed. It's no
mhm,
limitation for information to be transmitted, for forces or for anything, for energy to. It can exceed easily the speed of light, but it. I think it's a framework for the human nature. It's a framework of what we can see. This the difference. We have a framework of our perceptions about reality are uh, limited to this speed, but the real world is not limited.
mhm,
So this is why we have, for example, quantum effects. The quantum effects, I think, are just things which are transmitted, energies which are transmitted, forces, energies, information, doesn't matter how it are called, but transmitted with speed bigger than the speed of light. And we cannot observe these things. For
mhm,
us, it's a limitation of observation. We cannot observe what is exceeding the speed of light. So then, if you have beyond our observation these things, for us, these things appear like superposition, quantum entanglement, and other quantum effects, which are not. In reality, there are no separation between uh, these effects. In these effects are like separated phenomena, or I don't know. It's a particle exists here and here in the same time, but I think because it exceeds the speed of light, it's not visible anymore, and this is why for us it's like a separated. In our perception, there are
mhm.
some separation in space-time, which are
So,
creating the relativistic effects for us. But this exists
okay.
often in perception, in experiments also,
Mhm,
because our experiments are limited to human nature, possibility to obtain information from the universe at the maximum speed of light. This is why I think.
So what Einstein did was he was right in a sense, but
Yeah,
he had a false assumption. So if
exactly.
you if you assume light has a speed, then yeah,
Yeah,
everything about special relativity does actually follow logically,
yeah.
uh, and time dilation and everything. But if you
And
don't assume that, then it doesn't follow logically. And so there's just one critical assumption there at the heart that I think is wrong. But also, when it comes to entanglement, I think there's two problems with that. So one is I don't think there's a problem with say particles communicating faster than the speed of light. In principle, I think they could do that, but I don't actually think there's communication going on, and here's why. So we know that there's some sort of what you might call a conspiracy between particles, right? They both end up agreeing with each other somehow, right? They're both related in a way that makes it seem like they must be communicating. But the first thing to establish is, well, which direction is the communication happening in? So is particle A communicating with particle B, or is particle B communicating with particle A? So where is the influence? Which direction is the influence? I think it's neither. I think there's perhaps a third variable which we don't know anything about, which is so A is not causing B, B is not causing A. There's a third variable causing both, and that's why we see a
maybe,
correlation.
maybe.
And I don't think the temporal order matters. I don't think it matters which particle we look at first, which one it gets observed first. I don't think that matters. They're both
Yeah.
determined in advance.
Yes.
And we have to really get into questions like, what do we really mean by randomness? Because I don't actually think there's any randomness in reality. I think randomness is really just a limit on our ability to make a prediction. So there could be many reasons why we can't make a prediction, or why we can't see a pattern. But that doesn't mean there's actually no pattern, or actually something's in principle unpredictable. It's more of a practical thing. Like we just don't have the time, or we don't have the information available to us. But I don't believe in real randomness, and a lot of people who study quantum mechanics do believe in real, that this is the only real randomness. I just don't think it is. I don't think randomness is real.
It's just what we can observe. It's not about the real thing, which is behind. Behind can be anything.
Yeah. The randomness is not in something physical. The randomness is the connection between the mind and the physical thing. So if I have a deck of cards and I randomize it, that just means I wasn't looking and I did a bunch of stuff and I wasn't keeping track. And now the connection between my mind and the deck of cards is broken. But if I look at the cards and I see them, okay, now I've restored the connection. Now I know what there is. That's all. There's no actual randomness. It's a connection between mind and matter. It's a
Okay, so what about this selection of the light? You said in your theory about this selection of light. Why is this
yeah.
happening, or how is this happening?
Oh, that's a really good question because I've put a lot of thought into it, but I haven't got an answer yet. So I know I'm in speculative territory.
Oh,
There's some things that I would like to know a lot more about, but it's very difficult to get good answers to my questions. I just want to be able to visualize, for example, how does ordinary transistor radio work? How does it receive a signal? I don't want to know it mathematically necessarily, but I want to know it in a way that I can really grasp intuitively,
oh,
because I think that would have a clue. So I know that a radio transmitter can pick up a particular frequency, right? And it will just ignore everything else. So there's electromagnetic
yeah,
radiation that's going right through my body right now. There's radio waves that are going right through my body. To me, it's as if they don't exist because they go right through me and I don't interact with
yeah,
them. So that's the way I think most light naturally is. Light, generally speaking, light doesn't interact with matter. It goes right through it as if it's not there. But the real question is, why is it possible to interact with light? Sometimes it obviously is. We can see light, right?
oh,
So uh, sometimes we can select a particular frequency. So our eyes do that, and your radio does that, and anything that resonates to a particular frequency does that. Most things that resonate, that pick up light, do so to a very narrow range of frequencies. So my question is sort of why, and what I think the answer might be, has something to do with resonance. So, like in a cave, you can sing a certain note and nothing happens. Another note, nothing happens. But then you hit the right note, and it reverberates, and you get this big sound. And I think that's sort of what's happening. There's a cave-like process. We used to model electromagnetic radiation like that, like it was a resonating cavity, right? So basically, there's something about matter that acts like a cave that picks up certain frequencies. And what I think is that there's a relationship between wavelength and frequency that allows it to pick up only certain combinations of frequency and wavelength. So there's a consistent relationship between frequency and regular. So basically, what I'm saying is we're creating a standing wave that has a certain relationship between frequency and wavelength. And if you have that certain ratio between frequency and wavelength that's consistent, that what you get from that is a speed. So that's sort of how we get the speed of light. That's what I think. I know it's not that clear the way I'm explaining it. Maybe I could do it better.
These are linked to, this is happening because anything, all the forces of the universe, not all the but the fastest forces of the universe we can perceive are transmitted with the speed of light. Gravity, for example, or
we don't know that.
Yeah.
We don't know that gravity. I mean, everyone says that over and over and over again, but we don't really know that gravity moves at the speed of light. It probably is instant. Now, it's hard to imagine how it could be instantaneous, but we don't have anything that can rule that out right now.
Yes, it
we have
any speed, but we perceive it like this.
Well, I would say we don't. It's not that we perceive it that way. It's that's what we think is true because that's what we've been told. There's no direct perception. We don't perceive gravity waves. There's people who claim to have measured them. They basically built this multi-billion-dollar noise detection machine, which allows them to find any pattern that they want to find, and they did find the patterns that they wanted to find. That's all I know. And you know what? When you got billions of dollars on the line, you can't say we found nothing. You just can't. That's not a viable option. So I take that with a grain of salt. So, and I'm very pleased to see that Sabine Hassenfelder is very skeptical about it as well.
So I think in all humankind experiments until now, we are missing one essential thing. We are not making experiments with things which exceed the speed of light. For example, so-called tachyons. If we would make these experiments with tachyons to detect something using tachyons, not light or not sound, not something which exceeds, then we would see in the black holes or under the Planck scale or something. I don't know.
All right. I have a question for you about tachyons. So tachyons, I know they're a hypothetical particle that moves faster than light. But what else do they do? Like, what are they used for? Like, I know what electrons do. I know, like, you could talk about electrons for hours talking about.
I think there are no tachyons there.
Yeah.
I think it's just normal matter, normal energy like us, but it's exceeding the speed of light normally, and we cannot perceive it anymore. So for us, it's becoming a black hole or outside of the visible universe or something, because we are obtaining information through this visible light, which it has a speed, and it's not possible to if we are using this method, then we have some limitations, and these limitations are creating in our perception inside experiments, material experiments, not just theoretical physics, are creating a wrong perception, a deformed perception of reality, of what is real. It's deformed. This perception is deforming reality with this, exactly with this Einstein relativity. This is a perception, a wrong, how our perception about the universe is deformed.
Yeah. The funny thing, I think part of the reason is it's the mathematical nature of physics. So, I mean, math is a very important and useful tool, but we can sometimes use it a little too much, and I think it creates problems. So, for example, I go into my next book a little bit about the concept of entropy, and I look at Boltzmann's. There's lots of equations that quantify entropy. But the way Boltzmann decided to do it, he had to make some arbitrary decisions. He puts a factorial here and then here, and you look into what does that mean? Why did he do that? And you really get into the nuts and bolts of it, and you realize this was a very dubious assumption. For example, he assumes that when you have a bunch of particles, and there's lots of different configurations you could put them in. The way he counts them such that if you were to take two of these particles that are the same kind of particle and swap their positions, that counts as the same. There's no difference, right? So in other words, he's imagining that these particles are merely bits of information. They're merely token, like coins or things that they're interchangeable, right? So if you think of it that way, of course, in the end, you end up with this theory that says that matter is really just information. Because from the very beginning, we've been assuming that it was information all along, right? So it's
perception, not in reality.
yeah, you sneak these little ideas and assumptions into the equation. Nobody notices that they're there. They just apply them. And what we end up with, it's like garbage in, garbage out, right?
And where is this leading to? This theory of Boltzmann.
Boltzmann, eventually, I think Leonard Susskind and Bekenstein and others have basically proved that it leads to the idea that the whole universe is a hologram.
The hologram principle.
Mm-hmm.
And the whole universe, it's a black hole.
Yeah, I think they're just basically showing that there are problems with the math, but they don't.
Okay, I have very interesting question. If the black hole conform to this calculation, it's a black hole. Where is the singularity? Where are we traveling? All the universe is traveling towards inevitable, unique central direction point, which is singularity, and we cannot escape to this. Where is this happening? Because the universe is like a black hole with this theory, but it's not looking like a black hole at all. We cannot see this.
Yeah, you can't prove that the universe is or is not a black hole, but I just think it's a weird idea. I mean, I don't really understand it that well. I mean, I get that. I don't see how we could be a black hole and how every black hole could have a universe in it. It's it's not a very coherent idea.
It's not.
But so let's go back to the information paradox. So the idea is, here's a thought experiment for you. Let's say we're playing a game of chance where we're rolling dice, okay? And we have, based on because we play these games all the time, we made a theory about it, right? So this theory allows us to calculate probabilities. Probability theory, that's a real thing, right? You can learn all about it, study it for years. Okay. So this has all been based on us playing dice or whatever, games of chance. Okay. We really believe in the rules of our probability theory. Then as we're playing dice, some squirrel comes by and takes our dice. Okay. Can we say that the squirrel has violated the rules of probability?
No.
No. That would be crazy. Why? Because when we made those rules, we didn't anticipate the squirrel. That doesn't mean the rules were wrong. They just don't include the squirrel. The squirrel messed it up. But you know what? That's okay. We can have that. We can have exceptions because it just, it would be kind of weird to say, oh no, that what we just saw happen didn't happen because that would break the rules of probability. But that's exactly what we do with black holes. right? We say we've got these rules of probability that make sense and work in other contexts. They must also apply to black holes. Therefore, the black hole can't destroy information. Well, I'm sorry, but I think it does destroy information. But you know what? Most of the time, it's not destroying information because all that stuff's happening in an environment where there is no information at all.
Okay,
If
so
we go by
what are these black holes then?
well, it's just a really heavy, dense object that it has a lot of gravity. The gravity becomes extremely intense in the vicinity of a black hole. That's all it really is. I don't have to accept general relativity to understand what a black hole is. There's Newtonian black holes,
Yes,
right?
yes.
We don't have to accept quantum mechanics either. We know that these extremely massive, dense objects can exist, and we've just recently been able to get images of them. But I don't claim to be an expert on black holes. The mathematics is quite demanding. It is an interesting subject, and you can spend your whole life studying them, just as Stephen Hawking did. But I don't think they destroy information because, firstly, what we're calling information is not what I would call information. If we want a separate term for it, we should have a separate term for it. But it's basically the idea is well, there's information entropy, which isn't even entropy, but it's a concept that Claude Shannon came up with to explain how information can be very random. But that's not just any information, that's information, real information that's been compressed. So if I'm communicating with you, I want to send you a message, I want to compress it so I send it to you quicker and you don't need as much memory to store it. Then you can uncompress it later. But when it's compressed, it's very random. It's hard to make sense out of it. You have to unpack it before you can actually read it. So that's not what a black hole does. A black hole doesn't compress information. It destroys information. But because we now interpret randomness as the essence of information, we think that whenever we see randomness, we're dealing with dense information. That's not true. I totally disagree with that. I think that's a really weird way to interpret reality. And it's just because we're inappropriately applying information entropy to the universe. We're taking an equation that works within a context of information theory, and we're applying it outside of that domain to the universe, and I just think it's totally inappropriate. Yes, we can find some interesting things. We can come up with some statements that sound really hard to believe and fascinating, but that doesn't mean they're true.
Yeah.
I mean, it gets students interested, it makes them want to study physics, and that's all great, but we are lying to them.
Yeah. Yes.
Reality probably is a lot more boring than the theoretical physicists make it sound. However, there are some things in my theory that are pretty interesting, like how is it that light can move at multiple speeds at the same time, right? How is it that light can be in a super velocity? That I don't really fully understand. I don't really understand a lot about quantum mechanics, right? Superpositions are very strange. But so I'm not trying to make physics boring necessarily, but I think actually physics could be simplified a lot and it could be made a lot more boring. But I think a lot of the voices, a lot of the top academics are making it way more complicated than it should be. They're hiding their assumptions in equations, and they're making it more mind-blowing than it really is. Because contrary to what we would think,
Sci-fi.
the harder it is to believe an idea, the more people would want to believe it.
Yeah.
In physics, unfortunately.
So the reality it's a Newtonian reality, and quantum physics relativity is just a wrong perception about this reality. I feel so. I don't know.
There's
It's
still a lot of, starting with Newton, there's still a lot that we need to fill in. There's still a lot that we need to understand, right? Newton didn't really understand everything. There's still a lot of mysteries. We still don't understand what it is, what this redshift that we're seeing means, and how the universe could be
Doppler effect also.
expanding. And we still don't understand dark matter.
Doppler effect, no?
It could be, but there's other things it could be too. Like the standard explanation now is that space is stretching, and so the waves stretch along with the space. But it could also be there's a tired light idea, which I see some merit in. I think what could be happening is there's some conflation between, like, what we get is the amount of energy in the photons, but there's some conflation between amplitude and frequency. So energy could be decreasing, and some of the effect of decreasing amplitude could look like decreasing frequency, but it isn't really. That's what I'm not convinced by that idea, but I think it's somewhat plausible and interesting. So I'm putting some thought into that. So if that's true, then the universe actually isn't expanding. It's just an illusion from the fact that more distant objects look dimmer.
Exactly.
And then they also look redder.
There are some physicists who said maybe this red shift, this which is experimentally proving this expansion of this accelerated expansion of this the universe, it's existing. It's just it exists. This redshift exists just because the light is traveling through gravitational fields, and it's just because of this is redshifted. Maybe because light is traveling, and this condition is making it to redshift, and this is
that's
why
definitely an element. There's lots of so that's the problem. Like in normal, if you want to be very sure about being accurate, then usually you want to have multiple ways of estimating something. So with speeds, we can use lots of different ways to figure out how fast is something going. But unfortunately, with very, very distant galaxies, we only have redshift. That's it. And redshift can mean 3 or 4 different things. So we're really scraping the bottom of the barrel to come up with these estimates. It's like, how fast is that galaxy moving? Well, we don't have a lot to work with. But I think we can potentially have more to work with. I think there's, the sad thing is, you look at a gigantic galaxy that's very, very far away, you don't see it move because it just looks like it's frozen in time. But if we put a lot of effort into it, we might be able to actually watch it move. We just need a really, really big picture, and we need to, look at it for a very long time.
Yes, exactly.
And then we can come up with something that can corroborate what we think or not. And that's why the new telescope is so important, right? Now we're seeing, we were wrong about everything. Exactly. Which shouldn't be that surprising, but it is.
Okay.
I don't know. So I know you said that there's a lot that you want to understand about my theory, and I'm not sure. I would like to fill in any gaps, like if there's any specific questions you have, like about what I am saying, what I'm not saying.
I wish to understand it in a very simple way, if it's possible. I saw your movies where you are proving mathematically Einstein is wrong. I understood something, but not everything.
Okay.
Not all. I have some problems about understanding this. So if it's possible to explain in a simple way how you prove this relativity is wrong mathematically.
Well, I think conceptually, okay, there's that. Experimentally, that will come later, but conceptually, I'm always coming up with new ways to describe it succinctly. And the way I'm doing it now is I say, I'm only answering 2 questions. 1, what is speed? Seems like a simple question. And number 2, how does light move? So Einstein has answers to those 2 questions that are different from mine. And those questions each pertain to the two postulates of special relativity.
Yeah.
So let's deal with the first question. What is speed? I say speed is a distance between 2 points in velocity space.
Yeah.
Einstein doesn't say that.
Well,
Einstein says it's something that only exists within a frame of reference. So something can have the same speed in all frames of reference. And according to the way I look at it, the same thing can't have the same speed in all frames of reference. That's not possible.
just a second. I don't understand what you said.
Yeah.
What
So
what is Einstein said and what you said with this?
So Einstein's idea of speed is that it's very subjective.
Yeah. So,
Because you do need it. He agrees with Galileo and Newton that you need a frame of reference. So the equation of distance over time equals speed, that's not enough. I think we all agree that's not enough. That was great before Galileo and Newton. But after Galileo and Newton, we know you need a frame of reference. Einstein says speed is something that's only true because it's like it's not just relative, it's subjective. It's true within a frame of reference, but it's something else in another frame. And that there's truth to that, right?
yeah.
The frame makes a difference. The frame is everything. It matters a lot. But I say, in addition to that, a speed is not just something that exists within a frame. It's also a objective relationship between frames, right? So my frame has a location in velocity space, and your frame does too. And the distance between our frames in velocity space is the speed. It's how fast you're moving relative to me, and it's how fast I'm moving relative to you. So everything hinges on this concept of velocity space.
Yeah.
If velocity space is hard to understand, then my theory is hard to understand.
No, this is simple.
Yeah.
I understand.
Okay. Yeah. Okay. So I've redefined. I say that based on insights from Galileo and Newton, where the frame is very important, I've redefined speed from just the distance over time equation to it's now a distance. It is a distance in velocity space, and that's the basis of my theory. Secondly, to answer the question, how does light move? I say light's in a superposition in velocity space. So Einstein would have it at it would be in like the velocity bubble, right? It's in a bubble in velocity space.
Yeah.
I say no, it's everywhere, and the bubble is an illusion.
Yes, I understand this.
So that's it. That's my theory. I say speed is a distance between 2 points in velocity space, and light is in a superposition in velocity space. But we only interact with the light that's in that velocity bubble around us. And as we move, our bubble moves with us. Almost like a shadow. So based on that, I don't require any concepts of time dilation or length contraction or anything to explain this stuff. That's all extra stuff that I don't need. And I also obviously have to get into, because every physicist really who studied the subject matter believes very strongly that we have lots and lots and lots of evidence for time dilation and length contraction. And I say, actually, there's better ways to interpret that evidence, and it's not as strong as you think. So it's like it's a mile wide but an inch thick.